overall, we really don't use cotangent secant, cosecant that much. I mean, we obviously know. So this is how I look at it. All right, so kind of graphing sine and cosines up here. All right, that's it for importance. Tangents down a little bit, then the other three are kind of down here. Okay, I at least want to talk about it. I at least want to do it. So you've seen it. I will not ask you to graph these though. Does that make sense? Yeah, I'm not going to ask you to graph these because they're tough and it's one of those. Um, I just I don't want to make you guys do something that you're not going to use much. You know what I mean? I think you guys will appreciate that as well. Where's my notes? There we go. Trig notes. All right, so let's start with the cotangent of x. Now remember yesterday we did tangent. What's tangent kind of look like? Looks kind of like the cubed function, just over and over and over again, right? Yeah, overall that's what it looks like. Cotangents sort of like that. So remember tangent is centered at your origin. It cuts through the origin, right? Because then we had a intercept at pi and negative pi, right? Or sorry, pi over 2 and negative pi over 2. But it starts at the origin. Cotangent is shifted a little bit from that. All right, so I'm going to go ahead. I'm going to we'll go pi and 2 pi, pi, 2 pi, and I'm going to go negative pi as well. All right, now I'm going to go through, so it'll be pi over 2, 3 pi over 2. So I better write them. Pi over 2, pi over 2, 3 pi over 2. All right, so this is going to be our key points. So this is what the cotangent is going to look like. We're going to have asymptotes at every value of pi. We would also have an asymptote. It also have an asymptote at the y-axis, but I can't really draw a dotted line on a solidon. Okay, so I'd have an asymptote at every value of pi. Now, if I have tangent that looks like this, what do you think cotangent is going to look like? It's going to be the opposite. It's an inverse function, right? So now, tangent goes low to high. This one's going to go high to low. Look like this. All right, that's what cotangent would look like. Same thing as before, same thing as tangent. After you find where the asymptotes are, the point halfway between the asymptotes is where you're going to cross the x-axis at. So in this case, we had an asymptote every pi, so a pi over 2 is where our intercept would be. Okay, cotangent looks like that. Our period was pi because we made one full cycle from 0 to pi. All right, our domain is going to be all real except multiples of pi, because every multiple of pi is going to be one of your asymptotes. And your range, that's all real numbers because it goes up and down forever. We have vertical asymptotes on this, and this is at, like we just said, at the multiples of pi. Your x-intercepts are going to be midway between the asymptotes. Okay? Midway between asymptotes. All right, then lastly, even or odd function, this guy is going to be odd because it has origin symmetry. All right, and then if you were going to graph this, you would want to graph it using the same process as you graph the tangent function. All right, remember that 4-step process? Just for a reminder. Step 1, find the 2 consecutive asymptotes. All right, you do that by taking pi over 2 is less than bx minus c is less than pi over 2, simplifying it so you get x in the middle. Remember doing that? Okay, that's what we did yesterday. That's your first step. Second step is to find your x-intercept, which is halfway between the two asymptotes you just found in number 1. 3, you find the quarter and 3/4 values in between that asymptote. Right, that gives you that intermediate point between from your x-intercept until it kind of goes off into infinity. And then with that, then you would graph a period and then replicate if needed. Okay, if they want you to do 2 periods, you would do two sets between the asymptotes. Right, so again, cotangent is not horrible. We can graph a cotangent if we absolutely need to. All right, so we can follow the same steps as a tangent. Where it gets a little bit tricky is secant and cosecant. Okay, and we probably are going to compress the period now. We talked too long on that worksheet. All right, so good if I move on to cosecant. Okay, so cosecant. Remember, cosecant is paired with what? Sine or cosine? It's paired with sine. Okay, it's the inverse of sine. So to graph your cosecant, you actually have to graph your sine first. All right, so I'm just going to flip to that last little point I have. So if I was going to graph this cosecant function, I would graph the sine function at the same value, and then graph the cosecant at the max and min values of the sine function. So if you were ever given something like this, y equals 2 cosecant 2x, I just made an equation up. What you would want to do is you would want to graph then, just change it from cosecant to sine. So you would then, when you would graph y equals 2 sine of 2x. And if you graph that guy, then you can use that graph to come up with your cosecant graph. All right, so what I'm going to do here, and all I did was just change it from cosecant to sine on the equation. So I'm actually going to graph sine first on this graph. So I'm going to graph this, change the color. You can see yellow, can't you? Okay. So my sine function, we'll do things on the axes first. Okay, so we'll do pi, 2 pi, negative 2 pi, pi. Then I have my pi over 2's here and here. Okay, and then pi would go -1 to +1. All right, so now we'll bring out the yellow one. So my sine would be here, 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 here. Oh crap. Okay, can we see that? So that yellow one right there, that is my just y equals sine of x. Okay, then if I want to graph the cosecant of x, it's going to have asymptotes as well. It's going to have asymptotes everywhere where sine has an x-intercept. Okay, so there'll be an asymptote here. be an asymptote here. There's one at the y-axis. There's one here. And one here. All right, so there's all the asymptotes I would have on that, 2 cycles. Then what you want to do is go to every min and max point and basically draw a parabola. Okay, so I start with this max point over here. It looks like that. Okay, you go to that max point, draw it up. Go to the min point, draw it down. Max point, draw it up. Min point, draw it down. And that is just the inverse of your function the whole way across. Okay? You look at it, what's it doing? It's doing the complete opposite at every point. All right? So, characteristics of that. What's that? It's the inverse, okay? So here is basically a parabola, right? From here to here, inverse, flip it. Think of it like sine. From sine to cosecant, you flip it, right? It's kind of the same thing when you graph it. You graph the one and essentially flip it everywhere. Okay? All right, so my period, 2 pi. My domain, all real, except multiples of pi. And that's where we have our intercepts at again. Range, this is where your range is a little bit different. It's all real, but y is either less than or equal to -1 or greater than or equal to +1. Okay, you have vertical asymptotes, multiples of pi. And then even or odd, this guy would be odd because it has origin symmetry. There's just all kinds of stuff going on in that graph, isn't there? It's all over the place. We got all the dots. Looks like we do color by number here. All right, last one. Yeah. Uh-huh. Would you have to draw the sign? You would have to draw the sign to be able to get the cosecant. You could find the min and max. All right. I like to especially draw it here so you guys can see what it is the opposite, but you could get away with it without drawing the dotted line through, yeah. On a test, I would not ask you to graph it. Now there might be a picture like this, and I would say this is what function. You know what I mean? You can say cosecant, secant. So you just look at it and be like, all right, well, it doesn't pass through the origin, right? This doesn't pass through the y-axis, so it has to be related to sine. Okay? Sine passes here, here's the min. So then secant would be very similar in concept, but what do you think secant's paired with? Cosine. There we go. Okay? Let's do it, and we're done for the day. So graph the secant function, same type of thing. Graph cosine first, and then go to the min and max points, draw your parabolas. Okay? So you go pi and 2 pi. We'll try to do this one a little quicker. Boom, boom. It's just kind of hard to graph these guys. Boom, boom. Okay, we're going from -1 to +1. All right, cosine, we are at your max point at your y-intercept. Okay, so it looked like that. And this. I'm going to draw this. I'm going to draw cosine again in yellow. Okay, there's cosine. So then we're going to have our intercepts again, or our asymptotes are going to be everywhere that there's an x-intercept, same as before. There's going to be one here. There's going to be one here. There's going to be one here. And there's going to be one here. Okay? And then go to every max and min point. Essentially draw a parabola. Okay? Facing down, facing down. Facing up, down, down. Now I'm going to draw at the ends here. There's only half of it, but I'm going to draw half of that parabola as well. All right? Questions? That's still pretty though, isn't it? All right. When you graph these trig functions, oh man, they're beautiful. I should put them on the walls in my basement or something someday. What do you think? All right, so here's the characteristics really quick. 2 pi, domain, all real, except multiples, not pi, but pi over 2 on this guy. Okay, range, it's going to be all real except less than -1 or greater than 1. Okay, vertical asymptotes at, we're going to call odd multiples of pi over 2. I'm going to say odd because it'd be pi over 2, 3 pi over 2, 5 pi over 2, and so on. All right, because 2 pi over 2 would still be a multiple, but that would just be pi. And then even or odd, this guy would be even because it has y-axis symmetry. Questions? Y is less than or equal to -1, or y is greater than or equal to 1. All right, same thing, graph cosine, draw from there. All right, that's it for today, guys.